So you remember our goal is to take the mixture Gaussians generative model, um, fit the parameters of that model by using maximum likelihood, and then infer to which cluster every data point belongs by computing the probability that it belongs to the cluster K given the parameters that we've learned and the value of the observed data itself. And in this video, what we're going to do is we're going to start to talk about how we can go about learning the parameters of the model. So how do we actually carry out maximum likelihood learning in the mixture of Gaussians generative model? And that will involve learning these three sets of parameters: the pi's, which are the chances of coming from each one of the clusters, the fraction of data points belonging to each one of the clusters, the mu's, which are the means of the clusters and play the same role as the cluster centers, and the covariance matrices. And we're going to be thinking about how we're going to solve this problem from a high level perspective. And I'm going to compare and contrast a couple of different ways of doing it. And that will form the motivation for the subsequent lectures on the expectation maximization algorithm. Great, so the first step we're going to look at is how do we actually compute the likelihood, and we'll see that it is tractable for this particular model, and it is closely related to a calculation that we computed for the toy example, where we try to identify which of the three pictures corresponded to the particular mixture of Gaussians model that was specified above. So if you haven't seen that video, there might be a good starting point. Great, okay, so here's the object that we want to compute. We want to compute the probability of all of the data points, x1 through to x big N, given the parameters theta. And this is the quantity we'd like to maximize as a function of theta, i.e. it's the likelihood of theta for maximum likelihood learning. So let's sort of dive in and compute this for our particular model. So the first thing that we might want to do here is realize that the data points are generated in an IID way from the model. You generate each data point afresh, and if we permuted the order of the data points, that wouldn't change their joint probability because they're drawn independently from the model. So we can write the probability of all of the data in terms of the product of the individual data points. So that's what I've done on the first line here. And then that product can come outside of the log and turn into a sum here. So this is making things easy for us because sums of logs are much easier to handle than products of things. So the log has come to our rescue again and turned this product into a nice sum. Now we're going to focus on this object in here, the probability of just a single data point, given the parameters theta. And this thing we can write out using the sum rule as the sum on k, probability of xn and Sn equals to k given theta. Okay, so this is just the sum rule where we're summing out over all of the possible clusters that data point xn could have come from, and summing up all of those probabilities just gives us the probability overall given the model parameters. And so that's what's been substituted in here to derive this next formula at the end here. So we're close to being able to relate this to our model. And the next step is going to be to substitute in here the product rule. So that's what I've done down here. I'm going to substitute in the product rule and say this thing is equal to the probability of Sn equals to k given theta times the probability of xn given Sn equals to k and theta. So this is, yeah, as I said, product rule. And these are things that are both specified by our generative model. So the probability of coming from cluster k given theta, this thing is just defined to be pi k. And the second one, the probability of xn given Sn is equal to k, well, that's just our Gaussian. If we know which cluster xn comes from, then its probability is just given by a Gaussian. This is this thing, so we're running out of space here. Great, so I can substitute those things in, which gives us this expression down here. And there's a little bit of a typo here. This is assuming a scalar mixture of Gaussians over a 1dx. In general, this would be a covariance matrix in here. Okay, so this shows us that the likelihood is tractable. We can compute it. What we'd have to do is for each data point, we compute its density under each one of the components, each one of the clusters, multiply that by how likely it is to come from each one of those clusters before seeing the data, which is the pi k's. We sum it all up, and then we compute the log of it. And we do that for every one of our data points and sum them all together. And that gives the probability of the data given theta, i.e. the likelihood of the parameters. So it would be perfectly possible to carry out direct gradient-based optimization of this log likelihood. So for instance, we could use something akin to gradient ascent, whereby we compute the gradients of this quantity with respect to theta. So we compute this thing. And then we could perform some gradient-based update using that computed gradient. For instance, we could use gradient ascent. So theta new would just be equal to theta old plus some learning rate, where this thing was evaluated at theta equals theta old here. We could compute some gradient-based optimization like gradient ascent on this thing. We'd have to be a little bit careful as we did this, because notice that the pi k's have to be positive, and they have to be between 0 and 1, and the covariance matrices have to be valid covariance matrices. So they have constraints in them. Their eigenvalues have to be non-negative, things like that. So we'd have to be a little bit careful, but it would be doable. We could just carry out some form of gradient-based optimization, which respected the constraints on our parameters to make sure they were valid probabilities in the case of the pi's and valid covariance matrices in the case of all of the covariance matrices. So that is not what we're going to do, although it would be perfectly feasible. We're actually going to take a second approach, and that second approach is going to be explained in subsequent videos, called the expectation maximization algorithm. And I want to be really clear up front about why we're doing that. We're not doing it because it's necessarily a better method for fitting, in fact. So in general, the direct optimization method that I talked about, so such as the gradient-based optimization by a gradient ascent, that would generally be faster. It will converge faster, and on modern computational frameworks like PyTorch or TensorFlow, it would tend to be faster computationally and easier to implement as well. But the reason why we're going to focus on the EM algorithm is sort of threefold. Firstly, it's sometimes easier to implement than the direct optimization method, or although as I said, the sort of modern computational frameworks make that less of a factor. EM is incredibly widely used. So you'll find it whenever you come across packages or previous implementations of work. So one reason we're going to focus on it is purely because you're going to encounter it all over the place. And I think you could probably go and code up the direct optimization method anyway. So it's better we focus on the thing that you haven't encountered already, the EM algorithm. And then thirdly, and most critically, the perspective from EM, in particular the connection to variational inference, is going to lead to incredibly important generalizations, and the objects that we encounter and the EM algorithm itself can be generalized to non-linear, non-simple distributions, so it can go outside what's called exponential family distributions. It can be deployed to a much wider range of probabilistic models. So this will get picked up again in other courses down the line. But we want to sort of put the foundations in here so you understand some these sort of more general concepts in the context of a fairly simple problem like clustering. In order to proceed to the EM algorithm, we need to introduce one new piece of mathematical machinery that you may not have heard of before, which is called the callback libeler divergence. So I encourage you to watch that video next before watching the video itself, where we start to talk about this second way of carrying out maximum likelihood learning, the expectation maximization algorithm. So watch KL divergence introduction first, and then we'll move on to the EM algorithm itself.